orders. So on Monday and in the lab on Tuesday, you learned that you can get reaction orders, so the exponents in a rate law. You can get those reaction orders by doing an initial rates method experiment, okay? There is another way. Another way is to study the mechanism of a reaction, okay? And I'm not even going to get into that. So that's an organic chemistry thing. And that's even some advanced organic chemistry stuff where you talk about, reaction mechanisms and all that. Reaction mechanisms attempt to explain at the molecular level how a reaction is occurring. So what are the collisions that are occurring? What are the bonds that are breaking? How many steps does the reaction happen? In Chem 101, when you learn to balance chemical equations, okay, this can be super duper misleading. Okay, here's why this can be super duper misleading. When we look at a balanced chemical equation like this one, it looks like what's happening is NO2 is reacting, slamming into CO, and we get NO and CO2 in one step. But that's not what a balanced chemical equation actually is. A balanced chemical equation just tells you essentially the net result of a reaction. These two things got changed into these two things. But it doesn't necessarily mean that the reaction occurred in one step. For example, this reaction has been pretty heavily studied, okay, this reaction right here. And we actually believe that it happens in two steps. Now, I use the word believe because a mechanism can never be proven, because you can never see the molecules collide and the bonds break. But we can come up with evidence to disprove a mechanism, and we can come up with evidence to strongly support a mechanism. And again, I'll let your organic chemistry teacher talk about all that. Here's the moral of the story. Somebody has studied this reaction. What actually happens is two NO2s collide to make an NO3 and an NO. And then that NO3 that got made collides with a CO to make an NO2 and a CO2. This NO3, we don't actually know that it exists because it gets created and then consumed. We call that a reaction intermediate. So NO3 is being a reaction intermediate in that, we made it and then it got used up. And if you make it and then it gets immediately consumed, you'll never see it, right? So that's why we actually don't know that it's even a part of this reaction until we would study the mechanism. The other thing here to understand is that while two NO2s are reacting, we get one back. So it got regenerated. At the end of the day, and this is like Hess's law, which you should have gotten Chem 101, NO2 plus CO, so NO2 plus CO goes to NO and CO2. That's our net reaction. A balanced chemical equation is just the net reaction. It's not actually saying how the reaction occurs necessarily, right? For example, this reaction happened in two steps. When you study the mechanism, if you can come up with and say, hey, this reaction is a two-step mechanism, if we can determine which of these steps is the slowest, that's the reaction that really controls the rate of the reaction, okay? If we can determine which of these are called elementary steps, which of these elementary steps is the slowest, we call that the rate determining step, or RDS, then we can actually write the rate law right out of it. So for example, the reaction coordinate of the reaction that we just looked at would probably look something like this, where it's a two-step reaction, right? So here's the first reaction, and then here's the second reaction. If we can figure out which one of these reactions has the higher activation energy barrier, then that's the only one we have to worry about. Here's why. If you have enough energy to get over the highest activation energy barrier, then there's clearly enough energy to get over the smaller ones. It's like a roller coaster, right? If you got enough energy to get to the top of the highest hill, the gravity should do the rest of the work, right? So that highest energy, activation energy, or sorry, I should say that step with the highest energy activation energy, that is called the rate determining step, or RDS. Or RDS. And let me skip ahead here. For this reaction, it was determined that this second step, no, I'm sorry. It's determined that the first step of that reaction was the slowest one, the one with the highest activation energy barrier. And here's the cool thing. If you know the rate determining step you can actually use the coefficients from the balanced reaction of that elementary step, and those coefficients become the orders in the rate law. Craziness. Listen to me. If you study a mechanism, you only have to worry about the slow step because that's the one that's going to control the rate. And we can write the rate law from the reactance of the slow step where the coefficients become the exponents. So these both have a coefficient of 1. So this would be NO2 to the first times NO2 to the first. Now this reaction, because they're both NO2, we could simplify. NO2 to the first times NO2 to the first is NO2 squared. So this reaction has a second order dependency on NO2. The other stuff would be 0 order. So that CO reactant, 0 order. Okay? So mechanistic studies offer you an alternative to doing the initial rates method to determine the orders. For example, if we look at this reaction is believed to occur in a 3-step process. Look, we got a reaction intermediate here. We got another reaction intermediate here. This would be 2NO plus 2H2 goes to N2 plus 2H2O, right? That would be the net reaction. But what's the rate law for this reaction going to be? Well, the rate law is we focus on the slow step. We look at the reactants from the slow step, and we could write that the rate law for this, the rate would be equal to the rate constant K times the concentration of H2 to the first times the concentration of N2O2 also to the first. Why? Excuse me, why are these to the first? They're to the first because these have a coefficient of 1 right there. Now, again, this method only works if you've studied the mechanism and you know the slowest step and you balance the slowest step. Then the reactants are the only thing involved in the rate law expression from the slow step, and the coefficients become the exponents. We said earlier that the rate of a reaction depends on 3 things. Depends on concentration. That's what we talked about on Monday. We just got done talking about temperature. We said temperature increases the rate of reactions. That's that whole, Arrhenius plot. We get the rate constant at different temperatures, blah, blah, blah. But now we need to talk about molecular orientation. The third factor is that molecules need to collide at the right angle and the right atoms need to hit in order for the reaction to happen. What that means is even if the 2 particles have enough energy to overcome the activation energy barrier, if the right sides of the molecules, if the correct atom from this molecule and atom from this molecule, if they're not hitting, then you're not going to have a reaction anyway. For example, if we look at this reaction right here, here we have a reaction between 2 NOCl molecules to make 2 NOs and a Cl2. Now, you have probably never thought about reactions before like this, okay? But let's think about it. In this reaction, we're essentially breaking this Cl to N bond, and we're making a new bond between these 2 chlorines. So if you think about it, how do these 2 NOCl molecules have to collide? Well, they have to collide where green hits green, right? Where the 2 chlorines have to hit in order to make that new bond, and then that energy is going to break these green to blue bonds. Okay, so what happens here is if these molecules, excuse me, collide with enough force to overcome the activation energy barrier, but it's not green to green, it's red to red or red to green, or you can think about the plethora of other options, blue to green, blue to blue, right? Whatever, right? If they don't collide at the right window of angles to create this correct bond, so there's probably a finite amount, like array of angles for these 2 atoms to hit correctly in order to get an effective collision. And this is called the molecular orientation, right? You have to have the proper molecular orientation in order for reaction that has enough energy to actually work. Okay, so that's kind of crazy to think about. Now, the coolest thing about molecular orientation is that it is actually how catalysts work. So y'all have probably heard of catalysts before, right? Especially if you take bio. I get a lot of bio majors. Boy, do they love talking about catalysts. But they don't even call them catalysts because the biologists, they got to feel important. So they come up with their own word for a word that already exists. They call them enzymes. So a catalyst in your body is called an enzyme. And I can almost guarantee you that every single person here who took freshman bio or bio 101 or 102 or whatever can almost guarantee you learned about enzymes, but your biology professor probably did a pretty terrible job of explaining how it's actually happening. So for example, as you can tell, I'm not super fond of biology, not my thing. I can almost guarantee you that in your freshman biology class, when you learned about catalysts, your biology professor drew a Pac-Man symbol up there, and they said, this is an enzyme. And then because your biology teacher either didn't want to or can't draw Lewis structures, they think that all molecules look like squares, and they don't want to be bothered with nomenclature because either they don't want to do it or they can't do it. So they don't name the molecule. They just call every single reactant a substrate, right? What a joke. So they call this a substrate, and then you learn square, fit, Pac-Man, make reaction happen good. Okay, and then maybe even learn some other crap, right? About feedback inhibition, where like you can have a competitive inhibitor where like pentagon, fit, active site compete with square for reaction. And maybe if you had a decent biology teacher, maybe they even taught you about a allosteric inhibitor, right? Where like triangle jams into side of Pac-Man, denatures the site of the active site. That looking familiar to you? Right? That's bio for you right there, folks. Okay. But let's talk about how this actually happens. Okay. What a catalyst actually does most of the time is it actually directs the proper molecular orientation. So, for example, an important catalyzed reaction in your body is reactions catalyzed by carbonic anhydrase. So, carbon dioxide in your blood reacts with water to make carbonic acid. So, we can get carbon dioxide, out of your body. Okay. Um, and the way this actually happens, if you study enzymes, you'll find that active sites tend to have a lot of nitrogens, oxygens, and even fluorines in them. And the reason for that is pretty obvious. Those are the three atoms that are able to hydrogen bond. And in this reaction, what actually happens is the active site of the catalyst bonds with the substrate, in this case, water, and it holds it there. So this catalyst has some oxygens and nitrogens in the active site that are able to hydrogen bond to the water molecule. Now, why is that important? Okay. Well, essentially what it does is it holds the water molecule out there and it says, hey, carbon dioxide, hit this. And it exposes that oxygen. What has to happen in this reaction is the carbon dioxide has to collide with the oxygen of the water. So the carbon from the carbon dioxide and the oxygen from the water are what have to hit. They have to collide because you're going to make a new C to O bond in this molecule. So what the catalyst does, or the enzyme does, is it holds the water molecule out there, and it makes it a much higher probability that the carbon from carbon dioxide is going to hit that oxygen. It also starts to weaken these bonds that need to break as well. So it does really two things there. So what do catalysts do? They actually, what they do is they lower the activation energy barrier. So if we looked at this typical activation energy barrier for this reaction, here's my H2O and CO2. Okay, here's my product H2CO3. Maybe this is the uncatalyzed reaction. So that's the uncatalyzed. What a catalyst does by weakening bonds and directing the proper molecular orientation is it allows it allows the reaction to happen with less energy. So the catalyzed reaction maybe only has an activation energy barrier like that. Now it's important to understand whether a reaction is catalyzed or not. The reactants are the same, the products are the same. The total change in enthalpy for a reaction is the same. The difference is the activation energy. Here's the activation energy for the uncatalyzed. Here's the activation energy for the catalyzed. catalysts are able to lower the activation energy for a reaction, which is going to make the reaction happen faster because now more collisions are fruitful collisions. Okay. Catalyst is able to lower that activation energy, usually by directing the proper molecular orientation. Okay, so that's where that factors into it. Also important to understand with catalysts is that they are not consumed in the reaction. So as soon as the reaction happens, it lets go of the substrate, in this case water, and then a new substrate molecule or water molecule can come in and react. Yeah. How we feeling about that? Oh, if you want to actually see what carbonic anhydrase looks like, I'll show you. So this is the actual like X-ray crystal structure of carbonic anhydrase. Okay, it's a giant macromolecule, as enzymes are. And here's actually the active site, and you can see the blue things are nitrogens. Okay, and we're able to hydrogen bond with our substrate in here and make the whole thing happen. So it's pretty awesome how that takes place. So it's just catalysts are just, or enzymes are just gigantic catalysts. Now, chemists, when we use catalysts, is usually like a metallic surface or something. It's way simpler than these giant macromolecules, but nature has had a huge head start. Some chemists actually are starting to use larger molecules to catalyze reactions. Like Jacobson at Harvard is using bifurcated molecules to do this, but nature's had a few million-year head start on us chemists. So these molecules tend to be a little more effective. It's pretty amazing.